Okay, so now we're going to take a look at one of the earlier theories of the atom. And believe it or not, one of the candidates of atoms that they chose to study was the simplest atom, which was the hydrogen atom. And Niels Bohr, who's this theory is named after Bohr's theory of the atom, is the one that came up with a lot of, at the time, sort of groundbreaking ideas, but we've since updated a lot of Bohr's theory to reflect what we know about the atom today, but there's still some concepts, some ideas that we can still use up to this day to help explain some of the observations that we make when it comes to atoms. So one of the earlier things that people notice, and you even notice this today, is that if you have sunlight, for example, and let's say, there's a rainstorm that goes by, so there's your sun, okay, it's shining. Imagine that this is a spherical, and then you have some clouds, in the sky, for example. Sometimes what you see is you see something that looks like this, right? So it looks like a rainbow, which we've all seen. And what colors do you see on that rainbow? Well, you actually see all colors of the color spectrum, and it looks continuous. Okay, so what's actually happening when you see a rainbow? Well, the sunlight, so the white light that comes from the sun, hits the water droplets. And what happens is that that incident light, so the sunlight, for example, as they hit the water droplets, the sunlight gets broken into its component colors. So all of the colors that you see in a rainbow, those are all the colors that make up the light from the sun. And it's the same idea. If you had, if you were looking at something that was glowing red hot or white hot, for instance, and you did something similar to it. So if this is a glowing red hot or white hot iron bar, for example, if you were to shine that light through, if let's say we didn't have water droplets, but let's say we use something that was similar. So for example, a prism, which does the same thing. Okay, the water droplets and rain, they function as they do the same thing. So you can think of these as lots and lots of these tiny prisms. And what they do is they break or they separate the light that's coming into the prism into its component colors. And what you would actually see is also here, you'll see a rainbow, which means that you're seeing all the colors, and it looks continuous as well. Okay, so what we refer to that is, we refer to that as the emission spectrum, because that is the light coming out. Okay, so emission meaning the light coming out from something, the light being released from, in this case, the iron bar. And the spectrum, so this part of the term here is just what we see. Okay, so we would see, for example, that rainbow. We would see the rainbow from in the sky, for example. That's the emission spectrum of sunlight or the glow from a white hot piece of iron, for example. And because we see all the colors, this means that all of the wavelengths of visible light are present in that sample, whether it is the glow from the iron bar or whether it is the glow from the sun. It's the same idea. So it's continuous, and that's really, really important when we compare the other samples or the other situation that we're going to talk about. Okay, so it's continuous. We see all the wavelengths of light when we pass that through a prism, for example, that's able to separate that incident light into its component colors. Now, what we've since noticed is that if we do something similar to, let's say, individual elements, we actually observe something very different. So for example, here we have a high voltage source, and it's connected to this tube, and this tube is sealed. And in here, what we have is some sort of an element. So let's say it's hydrogen gas in there. Okay, and with the high voltage, what we do is we provide energy. Okay, so we give the hydrogen a bunch of energy. We zap it with electrical energy, in other words. Okay, so remember in the sample, we have hydrogen atoms in here. And when these hydrogen atoms absorb that energy, they also then start to release light, or they emit light. And if we force that light through a little hole in here, so we have just one singular beam of this light, and we pass it through the same thing, like a rainbow, how a rainbow happens. So here we have a prism, right, instead of a water droplet, but it does the same thing. What we see is that that light that comes out of this excited hydrogen gas, we just gave it a bunch of energy, we don't see a continuous spectrum. So we don't see a rainbow, a continuous rainbow. Instead, what we see is distinct or discrete lines. Okay, so discrete or distinct lines. So it's not continuous, like we don't see all colors of the rainbow. Instead, in this case, we see one, we see two, we see three, we see four individual lines of different colors. And that's known then as the emission spectrum of that sample. Okay, so whatever that sample is in this discharge tube here, when we zap it with some electricity, we give it some electrical energy, or it could be heat energy as well, which is what we'll do in the lab, for example. We give it a bunch of energy, light is released, and then if we force that light through some sort of a prism, we see this line spectrum. So these different colors that we see correspond to specific wavelengths of light. And what we've since noticed is that depending on what element we put in these little discharge tubes, each element is going to give you its own unique line spectrum, right? So we call that an emission spectrum. And specifically now, right, we're just seeing lines. So we call it a line spectra or the line emission spectrum of that sample. So for instance, if we look at something like neon, which is, you think of neon signs, right? They have a very characteristic color associated with them that you see with your eyes. If we were to take that light and pass it through a prism, we would actually see these distinct, these individual lines. We have a bunch of oranges and reds and yellows, greens and blues that we would see. But when you look at a neon sign, it looks very orangey, right? But it's actually made up of these different colors. So each element is going to have its own unique spectrum. And guess what? We can actually now we can think of the line spectrum as a fingerprint for that element. Whatever that element is, in other words, now we can use it to identify the element. Just like you can use fingerprints to identify people, we can use these line spectra, these emission spectra, to identify, say, this element is present or that element is present. And this may seem very simple, but it's actually very powerful because we can, with the right tools, we can explore, we can examine the light coming out from distant stars and galaxies. We can do something very similar, and we can say with a high degree of certainty what elements are present in those stars, billions of miles away, just by comparing them to these fingerprints of elements that we know, and where we know what their line spectra is going to be. Okay, so when scientists say, when astrophysicists say, oh, there's a bunch of helium in this particular star in this galaxy, they're not just making that up, right? They're using instruments, very powerful instruments, to take that light, pass it through some sort of a prism, and get that line spectra that they can then match up to known elements, which is, when you think about it, that's kind of cool. It's very powerful, it's very simple, but it's very, very important. So these line spectra for the different elements, again, we can think of them as fingerprints. We can use them to identify what the elements actually are. So now when we think of, what's happening on a submicroscopic level, and the really the characteristic, the hallmark of Bohr's model of the atom is based on, okay, so Bohr's theory, and he used hydrogen because it's the simplest atom. There's one electron in it of the hydrogen atom. Okay, you can think of this as an analogy. Sometimes you'll see the term planetary model because it kind of uses the solar system as the basis. So if you can imagine an atom, and at the very center of the atom, you have the nucleus, and then you have your electrons that are not in the nucleus. And what Bohr said was that the electron actually resides. Let's see if we can make this more circular. In these, what are known as orbits, just like a planet orbits the sun. You can think of the nucleus as the sun, and then you have your electron that orbits around, and you have, this electron residing in that particular orbit around this nucleus. Now, according to Bohr's model, if we were to give this atom some energy, okay, so if we give it energy, so whether that's heat or thermal energy or electrical energy, or maybe light energy, okay, what happens then is that that electron, this one here that's in that orbit, okay, so this is the term that Bohr used, and we'll put it in quotations. This electron can absorb that energy. Okay, so big E there means energy. And what it can do is it can then jump to another orbit that's a little bit further away. So maybe it jumps now to this orbit out there. And this orbit, this one in blue, has a higher energy. It's green. Now, what eventually can happen, so imagine, we're starting off with our nucleus, our electron that's orbiting the nucleus in this green orbit. We give it some energy, we give the atom some energy, and the electron absorbs that energy. As it absorbs that energy, we see that it becomes excited. And it jumps to a higher energy level or to a higher orbit. Okay, that now has a higher energy level. What eventually can happen is that that electron can now relax back down, back to that inner orbit. So it relaxes back down to the inner orbit. And when it relaxes back down, it goes from a higher energy now back to that lower energy level. And when it does so, obviously there's a difference in energy. What happens to that energy? Well, energy gets released as the electron relaxes. And that energy that gets released can be in the form of light that we can then see with our eyes. Okay, we can observe this light, and we can maybe pass it through a prism, and we can see what different wavelengths of light that's actually made up of, just like we did previously. Okay, so when you think about it, this model actually makes really good sense. We have these electrons that are residing in these orbits around the nucleus. These orbits correspond to energy levels. The further away you get from the nucleus, the higher the energy level of that orbit. When you give an atom some energy, whether you heat it or you shine some light on it or you zap it with some electricity, the electron or electrons absorb that energy. They they get excited, they jump to a higher energy level or a higher orbit, and then when they relax back down, they give off energy, they release energy, and that energy can be in the form of light that we can then observe with our eyes. Okay, so he attributed the emission, the release of energy by an energized hydrogen atom. So in other words, this particular electron here that's energized, and then it falls back down as it's dropping from a higher orbit now to a lower orbit with lower energy. It gave up an amount of energy. So a quantum of energy is what it gives up. We talked about the quantum term before. And Bohr showed that the energy then of the electrons in this hydrogen atom, we can actually calculate what the energy of that electron is by a very simple equation. So we have En, so the energy then that's being of that particular electron, so En over here, is negative 2.18 times 10 to the negative 18 joules times 1 over n squared. And what is this n value that we have here? So this n we can think of as the orbit. Okay. Another term that we'll see is energy level. Another term that we'll see is shell. They all mean the same thing. That n value, that we're going to come back to that later on when we look at quantum numbers. But for right now, we can think of that n value as being an orbit. Okay, and n is always a whole number. It's a positive integer. So in our example over here on the right side, we can think of that first orbit, okay? We can think of that as being our n equals 1. Okay, that's our first orbit, or energy level, or shell. And as we go further out, well, guess what? The blue one is n equals 2. That's the second orbit, the second energy level, or the second shell. Okay, so what that means then is as an electron, if it gets closer to the nucleus, what happens to n? Well, as we get closer to the nucleus, n decreases, right? So if you look at our equation, right, if we try to interpret how this value for the energy of the electron changes as a function of the value for n, and just thinking about where n is. So if n increases, if the n value goes up, what happens to this term here, right? So we have 1 over n squared. That's what that is. So if n becomes a bigger number, 1 over a huge number becomes a small number, right? So this value here becomes very small. You have this number in front that is not going to change. So as this term here becomes smaller, the energy of the electron becomes more small, but it's also, remember, this negative sign that we see here. So if n goes up, what we find is that the value, the En value becomes smaller in absolute, just the actual number itself. And then the converse would be true. Okay, so if n decreases, so if it becomes smaller, then En becomes larger in value. Okay, because if this denominator here, n, is a small number, then 1 over a small number gives me a big number. So a big number now times this thing will give me a fairly large value, but it's still negative, right? Becomes larger in absolute value, but still negative. So what we find then is that En, the energy of the electron, is most negative when n equals 1. So n equals 1 corresponds to that first energy level, and we say that we refer to that as the ground state, which we'll abbreviate as GS, ground state. Lowest energy state, lowest energy level state for the atom. And for hydrogen, that's the most stable, right? That's when the electron is as closest to the nucleus as it can be. That n equals 1. Or shell or energy level. Now, what happens as n increases, as we saw before, as n goes up, the stability of the electron decreases. Okay, and that's because now it's more energetic. Okay, more energy means less stable. And we just talked about that. The further away you get from the nucleus, the higher the energy level, more energy associated with that electron. So each energy state that is greater than n equals 1 is called an excited state. Okay, so we excite the electron. It goes from a ground state, which is the most stable, to an excited state, where it's less stable. We'll call that ES, excited state. So ground state, most stable. And again, this is for the hydrogen atom. As we increase the number of electrons, it becomes a little bit more complicated, but the idea behind it is still the same. So Bohr was then able to use this theory to explain the line spectrum of the hydrogen atom. And again now, thinking of energy being in these quanta, in these packets, they come in discrete packages or bundles of energy, we can now explain what's actually happening. So when an electron goes from the ground state, n equals 1, to an excited state, it is actually absorbing energy. Okay, and we saw that in our model up here. Okay, so we have our energy in the ground state, electron in the ground state, n equals 1. We zap it with some electricity. It jumps, it absorbs that energy, it gets excited, it goes to a higher energy level, a higher orbit, in other words. And then when it falls back down and it relaxes, it releases that energy, it emits that energy in a particular amount as well. And again, those amounts of energy then, these quantized movement of the electron going from one energy state to another, analogous to the stepwise, right? So if a ball is going down the steps, it can either be on one step or another step or a second. It can't be in between the steps. And the differences in energy level of the steps correspond to those quanta of energy. So we can now calculate what the difference in energy is of one energy level, going from one energy level to the next by an equation. And the equation's down here. We'll take a look at the equation first, and then we'll explain its different terms. So this triangle E, we read this as delta E. So delta E, and delta of anything means change in energy. In this case, E is energy. So delta means change. Between two different states. We have an initial state. Initial state, as the name suggests, is where we're starting from. And then the final state is where we're ending. Okay, so the initial state is denoted as n subscript I. So Ni is initial, and then the final would be Nf, n subscript F. So a couple of things to keep in mind. When we go from, or if the initial state is higher in energy than the final state, okay, so this term here, Ni is greater than Nf, well then delta E, the change in energy, is negative, meaning then that we're going to give energy to the surroundings. Whereas the opposite would be true. If the final energy level state is greater than the initial energy level state, we find that delta E is going to be positive, and this means then that energy is absorbed from the surroundings. So all of this is encompassed in this equation that we have here. So we know that delta E is equal to h nu, right? We saw E equal to h nu before. Well, delta E is the same thing. And it's now equal to negative 2.18 times 10 to the negative 18 joules. And now we have our initial and final terms thrown in here, okay? So we have 1 over Nf squared. So the final state, final energy level, in other words, squared, minus 1 over Ni, the initial energy level, squared. So the equation becomes a little bit more complicated, but these n, remember, these n values are whole numbers, are positive values. all we need to do is to substitute them into this equation. The most challenging thing is this up here, figuring out what's initial and what's final in our equation or in our situation. Now, this gives us the change in energy. What we can also do is we can now relate that to the wavelength of the light. Okay, so for example, we know that speed of light is equal to the wavelength times the frequency. Okay, we have our frequency here. So if we substitute c over lambda for nu into this equation, and we solve it for lambda, find it is that we can relate the wavelength of the light that's emitted or absorbed is equal to this whole thing here on the right side. Okay, we know what h is, that's Planck's constant. C is the speed of light. This is not going to change. C is not going to change. H is not going to change. The numerator here is not going to change either. The only thing that changes is the initial and the final state, right? The initial orbit, final orbit, whatever that is, we just substitute that into our equation. So for example, if we take a look at, a special case now, or an example of the hydrogen atom. So we have here, and this will be a much better depiction compared to my drawings. So we have our hydrogen atoms, right? N equals 1. These electrons are residing in that first orbit or that first energy level. As we zap them with some electricity or some heat, those electrons become excited. So what can happen first, for instance, is that the electron, they may go from n equals 1 to maybe the n equals 3 energy level now. Okay, so it's a little bit further away from the nucleus. So we have an excited electron in that n equals 3 level over here. What can happen is this can now relax, so it relaxes from n equals 3 to n equals 2, so it goes closer to the nucleus. This has lower energy, and the n equals 3 has higher energy. So what happens to the difference in energy? That gets released as light. So energy here is released, and that corresponds to this red line in the spectrum. Okay, what could also happen is when that atom gets excited, that electron could probably have jumped to maybe the n equals 5 energy level. Okay, so now it's excited. Electron is in the n equals 5, so way further away from the nucleus than the n equals 3 or the n equals 2. But the same thing can happen. It can still relax back down. And when it relaxes back down from a higher energy level to a low energy level, n equals 2, that difference in energy now gets released as light. And that light, for instance, can correspond to this purple line that we see. So if we compare those two transitions that we saw, over here on the right side, we saw the electron relaxing from n equals 3 to n equals 2, and red light was being emitted. Here it goes from n equals 5 to n equals 2, and here we have purple light being emitted. So what's responsible for the different colors of light? Well, it's the amount of energy, right? Remember, higher frequency, higher energy. So over here, for example, the purple light corresponds to a higher frequency or shorter wavelength compared to a lower frequency, lower energy, or longer wavelength, which is what the red looks like. And we can see that for other transitions as well. So the different colors of light that you see in the spectrum correspond to different amounts of energy of those wavelengths of light that are being emitted. So when it comes to the hydrogen atom, there are several transitions that we can see, okay, that we can observe or we can measure. And these are charted here on this diagram from your textbook. The ones that we're able to see, the visible light, right, would correspond to what's known as the Balmer series, where we have transitions from n equals 3 to n equals 2, n equals 4 to n equals 2, n equals 5 to n equals 2, etc. All the other transitions, they are invisible to us because they correspond to either the ultraviolet region of the spectrum, which is invisible to our naked eyes, or the infrared region of the spectrum, that's also invisible to our eyes, right? So the other series correspond to ultraviolet spectrum, ultraviolet part of the spectrum. So like down here, for example, where there's a huge amount of energy. Okay, so high energy, high frequency of that wavelength. Okay, so really short wavelengths of light. So we can't observe those with our eyes, or they correspond um, to the infrared. So the IR end of the spectrum. Okay, where we have low energy, uh, small frequencies, which correspond to longer wavelength. The only transitions that we can see with our eyes is a visible spectrum, which correspond to these four transitions here in the Balmer series, where it's going from higher energy levels to the second energy level. Okay, and that's shown in your table. So the Lyman series, ultraviolet, the Passion and the Bracket, those are infrared. We can't observe these. The Balmer series encompass both the visible and also there's an ultraviolet in there as well. Okay, so let's now take a look at an example of a question where we have to do some of these calculations. And it says to calculate the wavelength in nanometers of the photon emitted when an electron transitions from the n equals 4 state to the n equals 2 state in a hydrogen atom. Okay, so now we're looking at calculating the wavelength. Okay, so we're going to use our equation that we saw previously. So 1 over lambda equals 2.18 times 10 to the negative 18 joules over h times c. Then the important thing here is this part of the equation. So in order to figure out what NF and what NI are, we need to ask ourselves, where are we transitioning from and where are we transitioning to? So it goes from the n equals 4 state. So what that means is this is my initial. N equals 4 is initial, right? That's where we're starting from, which means then n equals 2 would be final. That's where we're ending up. Okay, so when we substitute those values in, the 4 goes in here. I'm sorry, that's initial. So the initial goes the second part of it here. So that'll be 1 over 4 squared. And then the final, that goes first. Final minus initial is how we find the change of anything. And that would be 1 over 2 squared. Okay, so our h, right, our Planck's constant, substitute that in. We have our speed of light. We can substitute that in as well into our equation. We have our 1 over 2 squared, right? That's the final minus the initial 1 over 4 squared. And we end up with our value for lambda 2.05 times 10 to the 6 meters. Now, one thing you want to keep in mind, right? This is not meters to the minus 1, but meters. I'm sorry, it is meters to the minus 1 because it's 1 over the wavelength. So when you do this calculation, okay, if you look at your units, we'll write this out so it looks a little bit easier to process. 2.18 times 10 to the negative 18. We have joules, and that's divided by Planck's constant, 6.63 times 10 to the negative 34 joules times second. And that's times the speed of light, 3.00 times 10 to the 8 meters per second. Okay, so the joules cancel, seconds cancels down here. Okay, so you have 1 over meters as your unit, right? And that makes sense because it's 1 over lambda that we're solving for. So the unit of length there is in the in the denominator. So what we want to do, right, is we want to now convert it because we want the wavelength in nanometers. We want to do a conversion to nanometers here. So what we want to first of all do is when we plug that into the equation, what we have actually found is 1 over lambda, okay, is equal to this. So lambda then would be equal to 1 over 2.055 times 10 to the 6th, okay? And that is then going to give us this number here, 4.87 times 10 to the negative 7. We convert from meters to nanometers, right? We have a metric conversion, and then we can go ahead and solve. So we get 487 nanometers. That makes sense, right? It's in the right ballpark for the wavelength of light in this particular example.